right, guys. So for those of you that are just sort of coming in right now, we're going to go over some a little bit more challenging mechanism questions today. This is something that you guys, some of you may have seen if you've gone over some of my old exams. It is a question that I asked on the Organic 1 exam. And as you're sort of going through this, we'll spend some time going through this. What I want you to do when you look at this problem is recognize that I'm not going to give you a problem that is something you guys can't solve. This is going to incorporate information, mechanistic insight that should be learned from other areas that you sort of learned. So looking at this before we just go really quickly through a couple things together. When you see a mechanism that looks at this, does anything specifically stand out as this reaction somehow being related to something that you've seen in the past? Yeah. Say that again? Well, so I see he's sort of pointing out that there has to be an elimination at some point because he's sort of looking at the product here, and he's looking at the starting material, and he sort of sees some type of elimination, ring opening of that epoxide, which may be what's taking place. That's sort of one thing. There's two functional groups in the starting material, right? There's a carbonyl and an epoxide, both of which are functional groups that you've seen. So you're not necessarily being thrown at something new. But when you look at these functional groups and when you look at the reagents that are being used in this reaction, as I told you, the byproduct of this reaction was nitrogen gas. There's a specific reaction that you guys learned that this should remind you of. Does anybody? What's that? Nitrogen gas? No. Nitrogen gas. Just remind you guys of any reaction. The reagents. Again, functional groups, you have a carbonyl, you have an epoxide. In your chemistry on carbonyls and epoxides, have you ever seen hydrazine before? You haven't. You haven't been reading chapters. Guys, yeah. It's a reduction, yes. You don't remember the name. But what kind of reduction mechanistically? What's that? What's that? Not Clemmensen reduction, yeah. Look at your computer to find that out. Yeah, it's the Wolff-Kishner reduction. Okay? So if you don't know where to start, Wolff-Kishner reduction is a reaction that we went over in class, and it's in your book, where you take hydrazine and a ketone, and what happens in this reaction? What's the product? You get an alkane, usually with acid, or usually it says sodium hydroxide. Oftentimes I made the comment that sometimes I like to think about the first being acid catalyzed, the second being base catalyzed, but that's the Wolff-Kishner reduction. You guys should all know the mechanism of the Wolff-Kishner reduction. Okay? All right. So spend a little bit of time on this. I want to see somebody getting somewhere close to the answer. certainly this acids. Here we have a fire alarm, or we have a freaking. It's unbelievable. We gave an exam once at a lecture hall, and it ended up being there was construction on a final exam right outside the room. It's like, what? I don't know. Whatever. I give up. So we need to know this mechanism. If we don't know this mechanism, we can't figure out this mechanism. Based upon the fact that it took you guys a long time to even recognize what this reaction is, I'm a little bit pessimistic about your ability to figure out this mechanism. So let's think about if we don't know what the Wolff-Kishner reaction is, don't know what the mechanism of this transformation is. If you recognize this, which is something that we've actually gone over and we've covered in class, and it's certainly in your book, and it's something that's come up in the past, we can try to go through this mechanism together. So what is the first step of the Wolff-Kishner mechanism? Maybe if you don't know a Wolff-Kishner mechanism, you look at what you have here and you look at the reagent and you think about some of the chemistry that you guys have learned in this class and the mechanisms of the reactions you've learned. What is likely to be the first step in this reaction? Yeah. Say again? So usually, yeah, so the way that we had showed it previously is I sort of broke it up in a two-step process to at least be consistent with chemistry that you're sort of well aware of. As it turns out, hydrazine is very, very nucleophilic. You don't actually need acid to do this. But if we do have this react with, say, acetic acid, that is going to activate our ketone. Once we have an activated ketone, what can we do? Speak up, I'm hearing people say things, but I can't hear it over the fans. Attack the carbon with what? What carbon with what? So the nitrogen is going to attack this carbon? Carbonyl carbon, right? Okay, charge nitrogen. Okay, so we've got an amine that's reacting with a carbonyl. It's the first step of the transformation. What can happen next? What's that? Okay, do we want to put it somewhere else? Guys, this is a reaction that's analogous. I've sort of made the comment. This is a reaction that is the core of carbonyl chemistry. This is so much of the chemistry that you guys learn is this reaction. If you can't get through this first step, the first part of this, you're going to be in big trouble. Yeah. There's proton transfer from where to where? From the nitrogen to the oxygen. Right? So we're just going to get a proton transfer, which again I've mentioned is not perhaps what's really happening, but for bookkeeping and for saving space, it's okay. By undergoing that proton transfer, what have we done? Created a leaving group, right? And our leaving group is water. So water can go away. Okay. What's the next part of this reaction? Is there anything specific about this carbocation that should be recognized? Got a resonance form. What's the resonance form? Double bond between the nitrogen and the carbocation. Right, this is simply a resonance form. And again, we'll have a proton there. And that can be deprotonated, right? And that can be deprotonated such that you have the imine. You guys need to know the mechanism of condensation. Again, condensation of carbonyl with alcohols generates ketals, or with aldehydes generates acetals. Condensation with amines generates imines. Imines. Okay? That's the first step of this reaction. Say again, we've got hydrazine and we've got our functionality here. So what's probably the first thing we're going to want to do in this reaction? Yeah. We're going to do the exact same thing we did before. I'm not going to go through the mechanism again. You guys have to know this. You're going to get condensation of the amine with the ketone. Okay? Alright, so I'm going to give you guys about 5 minutes to figure out, that's the first step, it's getting to there. I'm going to give you guys 5 minutes on your own to try to get from here to there. Go at it. So I drew it initially. It's there. I drew it. Does anybody think they might have it? Anyone? They may be close. Maybe. Anyone? You might have it. I've got one mechanism that I don't love, but it's okay. There's one mechanism so far that maybe I give a 10.8 scale, I might give 8 or 9 out of 10. I've seen one that's pretty good, not quite good enough. Maybe go through a few of these stuff. So what I think I'm going to do is I'm going to take a few, I'm not going to say whose is whose answers, but I'm going to take a few of the answers that you guys have. We'll go over the board, probably shuffle them up, throw a few of the answers that you guys have on the board. We'll discuss the answers and what some of the issues are with those answers. Because I think that what's happening right now is that this is so far, it shouldn't be. It should not be otherworldly difficult. My concern that I'm seeing with a lot of the mechanisms is when I ask questions like this, it's very common that some of the very basic fundamentals of chemistry start getting destroyed. Whether your mechanism is 100% great or not, so Gong showed me a mechanism that was pretty good. It wasn't. There was a few issues with it, but it was mostly right. There wasn't anything in it that I think was particularly egregious. I've seen a lot of other mechanisms right now where there's a lot of things that are, I think, egregious, like showing, for example, electrons going to a molecule, and then suddenly that molecule goes from neutral to positively charged, right? Almost like forgetting that lone pairs are in specific areas, or conversely, thinking that lone pairs are in a specific area. So pushing arrows to give you a bond that might reflect what the product is, but through doing that, ignoring the fact that there's other things there like electrons. So I've seen a few things like that. So what I might want to do is I might want to throw some of these on the board so that we can see them and hopefully make sure that we catch these mistakes that we don't make in the future. So again, my hope on a mechanism like this isn't necessarily that you're going to get the answer perfect, but the hope is that you start trying to get through the mechanism without having all the foundational stuff fall apart. When you got one step of the mechanism, when it's going from point A to point X, I'm looking for point A to point B to point C. And when you show your electrons, when you show your arrows being pushed, does B reflect what you're showing happening to A? Whether or not you can get to the end, what's more important to me, especially at this phase of the game, is does each individual step at least make sense? Does that make sense? Are you bookkeeping with your electrons? Are you bookkeeping appropriately with your charges? Okay? Okay, so I'm going to, does anybody think they might have it? Anybody else? All right, let me show you guys a few examples of things that I saw people doing, and I just want you guys to sort of recognize some of the mistakes that are being made. Okay? So in one of the examples that I saw, so I'll show you a couple of them, but I think again, a lot of it is seeing the forest for the trees, right? Like, you guys, when you're going through challenging mechanisms like this, it can be a tough battle, right? Because on the one end, you want to try to get to the product, and you want to sort of see the bond disconnections and everything else like that. But you don't want to start disobeying the fundamental rules of organic chemistry to do this. You don't want to start disobeying conservation of charge, conservation of mass. We're changing some of the things that are taking place. So one of the mechanisms that I saw did something like this. The person clearly recognized that they wanted, so there was some good sort of problem solving going on here. They recognized that that epoxide wanted to be open. They recognized that there was a proton source, right, that might help assist in that opening. And so they decided to get to perhaps an intermediate that might help them see that opening a little bit better. Okay? And so what they did was, and then they got stuck, because they just tried to do a proton transfer. Again, I don't love this, but from the standpoint of simply trying to see some bond disconnections, we got to here, right? And then what this student tried to see to perhaps help them out is they said, well, I'm going to ring open this to get to something that's a little bit closer to the product. I'm going to put my carbocation there. Okay, so they got to an intermediate that looked something like this. And that was all good and fine and dandy, but then they did something that wasn't so fine and dandy, is that they tried to help correct this negative charge, right, that was on here, and what they did was they pushed the electrons onto that nitrogen, hold on, and through doing so, that might be a way to go, except they made one mistake, and that was they kept it there. And then they drew the molecule like this, and they ended up putting a positive charge on that nitrogen. So what is wrong with this mechanism? is wrong. There's nothing wrong, in my opinion, here, except that I left out my negative charge there. Besides that, there was nothing wrong with it. So from a conservation of mass, conservation of, maybe we don't want to make a zwitterion, but that's not a big problem, especially if you're just trying to see what's happening. That ring opening, nothing really terribly wrong here, at least none of the fundamental basics. But this is where a big issue started taking place. And I see a hand being raised. What's the big issue here? Right, this person was probably more focused on the bonds forming than actually the electronics of the system that were at play. This, and again, conservation of mass, conservation of charge. The net charge of this species here is what? Neutral. And then suddenly, just by pushing electrons, suddenly we're at a double positive charge, right? You see how that's a mistake that can be made if you're really only focused on the bonds that are being formed, right? Because in and of itself, if you were to draw this molecule in a vacuum, right, you would ordinarily go ahead and try to put a positive charge there. But the problem with that is that there were two lone pairs over here. And those lone pairs didn't go anywhere, right? So those lone pairs should still be in this product. So then what should be the charge of this nitrogen? Well, negative, right? But there's this bigger problem with that nitrogen. And what is it? You've broken the octet, right? So again, we'll come back to this one because I think that the beginning strategy of this, from a seeing and visualizing what's actually happening standpoint, I kind of think this is up to about here. I think we were all good. But then trying to sort of move things around here, there was that mistake that was made. Okay, does everybody see that? So this is the type of thing that you guys gotta, sure that lots of you guys make this mistake. I know that lots of you guys make this type of mistake. So again, you gotta make sure that you're keeping track of your electrons and so forth. Yeah? Say, this. Yeah. Well, so somebody just brought up the point that if you see this problem here, and you know that you can't make this, well, then we start getting a little bit closer. It was asked, well, I can't be here, but if I push two electrons at the same time, if I push to here, and this is sort of not a real intermediate, but let me push that double bond there, right? And then you look at that, right? So now, if you simply recognize the mistake that was made, you recognize that those electrons shouldn't have been there, that there was an extra set, you can actually push it an extra step ahead. See, just by sort of focusing on what that mistake might have been, right? You get to something, this is the final product, but it sure as hell looks like we're on our way, right? That sure as heck looks like we're on our way. Okay, so this was one mistake that again, I think that once you recognize that mistake that was made, you can say, okay, well, this is too many octets, but when I push them here, I should push these there. Now I've got my double bond. I've got this here, and I'm pretty darn close, I think, to being able to lose my nitrogen and put a proton there. Yeah. Absolutely. Yes. And this is a comment that was made earlier with regards to carbonyl chemistry, right? How, from a mechanistic standpoint, showing the carbonyl in its zwitterionic form, if you will, with a positive negative charge, sort of helps you treat the reaction more like an E1 reaction in essence rather than an E2 reaction. And one of the big differences between an E1 and an E2, right, is whether you're pushing electrons at the same time or whether you're pushing them one by one. This you would not want to do, so as just was brought up, you do it all at the same time, right? And you go directly to this molecule here. Okay, so we're not going to finish up this mechanism here. I just want to show some of the other mistakes that were made. But again, hopefully you guys can recognize that. And I know that this mistake was made by sort of focusing on the bonds. And again, one of the tough things about organic chemistry is you got to make sure that you're seeing what's not there. Just because there's not a set of lone pairs drawn there, we don't draw all of our lone pairs everywhere, right? So this is one mistake that I saw. And again, these are the types of things that I hope don't start falling apart when you do these. Okay. So another mechanism that I saw tried to get to something a little bit closer early on. This is before the iminium condensation. This person thought that they could get fairly close to the product. And what they ended up doing, and again, I'm not doing exactly what people have seen, but it's the general sense. Right? It was a similar aspect of, hey, I recognize there's an epoxide. That epoxide probably wants to have a proton, so we're going to grade open and go to the product. And so what this person ended up doing is they said, well, I want propionate with hydrazine. And they did a lot of the same things that the other person did. So I'll just, if you saw what happened before, they in essence wanted to get to this intermediate here. And they hadn't done the iminium condensation yet. So what this person ended up doing was they said, I want to use these lone pairs. They recognized that having a set of lone pairs adjacent to carbocation, that they could perhaps quench that carbocation. So what this person did was they said, well, I'm going to go ahead and I'm going to shoot the electrons over there, right? But then as they were doing this, I think, again, I don't want to put the thought in this person's head, but if I could get in that head, I think that then what was happening was they were saying, oh, wait, I need to then have something on this oxygen. So I'm simultaneously going to have it get propionated. And the product that I'm going to have is going to be a molecule like that that's much, much closer to what we have. So again, you can sort of see the thought process behind what this person was doing. It had that double bond there. Well, if that was an alkene, I could push electrons over there. Oh, wait, but then that oxygen doesn't really have anything on it, and I know that oxygen, to be in a neutral state, always wants to have two things bonded to it, so I'm going to go ahead and give it something. What's the problem with this mechanism? Yeah. Yeah, I mean, so I think the problem here is solved, again, by seeing what's not necessarily drawn. So I think this is where oftentimes mistakes are made, is that you don't see stuff there, and then you sort of move on to the product or whatever, and you end up redrawing molecules without recognizing everything that's there. Okay, so let's draw those lone pairs, right? So one of these lone pairs, right, so now we're moving electrons here, and these lone pairs are going to go and propionate it. So where are the lone pairs respective to the product? Well, the lone pair that reacted is now in this bond. Okay? So that leaves how many lone pairs left? Just one. Right? So again, here's an example where that oxygen, without the lone pairs being drawn there, you might assume that there's two electrons there. You're just sort of paying attention to, where these electrons are. But the problem is, what's the charge? If we assume that there's only one lone pair there, what's the charge of that oxygen? +2. Yeah, so this is actually +2. And that makes sense from a conservation of charge standpoint, right? This goes back to conservation of mass, conservation of charge. What's the charge of this proton? If you just think about it being protonated, that's a positive charge, right? So the net result over here is +2, right? Based upon what the mechanism was trying to do. But the product was in fact neutral. So again, this is one of these instances where you start paying attention to the charges of the systems. You should sort of recognize, wait. Something's not right here. And again, you can see how that mistake can be made. I think that I see the thought process taking place there, but once you start digging in a little bit deeper and trying to sort of look at the lone pairs and pay attention to those lone pairs, the same thing happens with protons that aren't drawn. You guys will often forget that there's protons in certain places, and you'll draw a double bond to something where there'll be another proton. So you guys got to pay attention to these kind of things, okay? All right. So that's the issue with this one here. All right. Okay, so now I'm going to discuss a mechanism that was a little bit closer. And there wasn't anything drastically bad about this. So again, I kind of like this mechanism to a certain extent. I would give most credit. But this wasn't, I think the mistakes that were made here weren't necessarily as egregious, but okay, so this person, and again, this isn't exactly what happened, but I'm going to get to the sort of points of what I saw. All right? So this person took this condensed version of this molecule. They recognized one of the things that we had brought up earlier, right? And that was that we have to do an elimination of some type. Okay? And what this person then, I think, thought was if we're going to do an elimination, what an elimination entails is like a deprotonation followed by a leaving group. And in this case, the leaving group is really kind of what? It's the epoxide, right? It's the one bond of the epoxide. And so I think what this person was trying to do here was they were trying to say, okay, well, I need to get a proton. If I'm going to do the elimination from there, I got to get a proton there. And so what this person did was, in essence, they showed some arrows going around, but in essence what they did was they made the tautomer of this molecule, okay? Which I often think is a good first step oftentimes in these, in the Wolff-Kishner, is to recognize that there is a tautomer. What's a tautomer again? What's that? Yeah, it's basically a proton transfer. It's two molecules that are related simply by a proton transferring from one place to another. And in this mechanism, the tautomeric form was, I'll just draw it out. They deprotonated one of these. I'll just draw the hydroxide. They deprotonated one of these, right? And then I forget. And then they ended up putting the proton there. Such that the product that they had was this. Okay? And now that they had the proton, I'm only going to draw this over here to give ourselves more board space. So now that they have the tautomer, they said, now I'm situated to do my elimination. So basically, sodium hydroxide, I've got my proton that is next to what's essentially going to be a leaving group. And so what I'm going to do is I'm going to have the hydroxide deprotonate and do the ring opening. Okay, does everybody see that? And now we're at that same intermediate, basically, once we protonate it, we're at the alkoxide here. We're at the same intermediate that we were previously once we did that ring opening from that other molecule. And I think this is okay. I think that it's not really, I think that the tautomer is one way that you can go about this, but do you need to go to the tautomer? And again, I probably wouldn't even penalize for this in particular, but they push the electrons down here to put a proton here, which they then go ahead and they deprotonate again to do the elimination. So since you've already got that negative charge here, if you just draw the resonance form where you get the negative charge there, then you're already set up to do the elimination. So in fact, you don't necessarily need to draw the tautomer to do the elimination, but you could certainly do that if you wanted to. Okay. Now, one of the things about a Wolff-Kishner, the final step should be fairly easy. I'm actually okay with this mechanism. There's a few other ways that you can do it, but that's probably fine. In both cases, we got to a molecule that looks something like that, right? And what we can do, right, is we need to sort of complete our exhaustive reduction. Right? Does anybody remember in a Wolff-Kishner reduction, what's the sort of, well, final step in a Wolff-Kishner, if you know the sort of final step in the Wolff-Kishner, once you're here, you should be golden. Right? It should sort of scream what the answer is at this point. So what's the byproduct of Wolff-Kishner? Nitrogen gas. And so the fact that nitrogen gas is being generated in this process allows you to generate intermediates that you might not necessarily otherwise generate gas. Yes, so I think what you're saying, yeah. So you're saying elimination of the nitrogen. So how do we eliminate nitrogen? Well, usually when we do an elimination, we're eliminating an alkene, right? Or if we're eliminating from an alkene, we're going to an alkyne. So this is kind of like elimination, right? What's our leaving group? Basically all this, right? And this is the double bond that we're generating, and this is the proton. So it is in essence an elimination. And so whether you draw it, wanting to show that. When you deprotonate, right, you can put the negative charge on that nitrogen, but it is in essence an elimination. The leading group in this case is a carbanion. We're going to extrude nitrogen gas. Again, this sort of drives the process to the Chapelier principle, and then once you got that carbanion, you're just simply going to deprotonate. And you're going to have the alkoxide, and then you're basically there. Right? Does that make sense? Yeah.
What would you call this final step? It's like elimination.
Yeah, that's exactly what I would call it. I would say it's an elimination.
So you do this first before you react with the
And
alkoxide,
that's exactly so. And so you just got right at, well, not acid catalyzed per se, but I think you're getting to the mechanism that I would otherwise prefer. I think now that I'm looking at this, I think I would probably give this full credit if I saw this mechanism. But the mechanism that I think you're suggesting is, I think what I would have done, and I think maybe what you're getting at, is that once you do your condensation and you get to that tautomer, right? Now you can basically do the elimination. You never actually even have to generate carbanion, right? Because the moment that you generate previously, you generate the negative charge to subsequently protonate. But if you just simply think about the quaternion form, right, in this case, I don't know the stereochemistry, it doesn't matter what the stereochemistry there is in this case, although I'm sort of showing it in that way. But you eliminate, and the elimination is is really a double elimination. I know that's kind of crazy, but right, what's happening is in essence, somebody was asking me a while ago about, so usually we think about elimination, it's actually called, like, I think it's like an E2 prime or something like that, is what these are often called, right? So normally we're used to elimination chemistry where the leaving group is right next to the proton. Basically, there's two carbons in between, right? So this would be an E2 elimination. If you have the same situation, but you're separated by an alkene, which is ultimately what this ends up being, you could break it down step by step. You could show the mechanism, put the negative charge there, and then have the negative charge open it up, and that's probably what I would expect to see. But you can do the same thing here, right? Except that it's through a pi bond. So this would actually be, I think it's called like an E2 prime, I think is what they call it. Right? Where you deprotonate, but now you've got an allylic system there. Right? Such that in this case you generate an alkene. In this case you generate sort of a diene. Okay? So again, the point here is that you can sort of push them both at the same time. But you can break this down as well, and that might make it easier to see, because I bet you guys are all like, what the heck is he talking about? I can't see it, but let me break it down so maybe it's a little bit easier to see. The point is that if you do that same elimination that we did previously here, that you should know from your Wolff-Kishner, you would get to you just made it to that molecule which you guys had seen before. And this would happen if you simply did the elimination. Put the electrons on that. Now you've got a lone pair, now if you break it down, hopefully you'll see it a little bit easier rather than showing it all in the same step. Yeah. These? Hydroxide. Yes, so nitrogen, triple bond. Yeah, so it would be the analogous, that's what I was saying, it would be the analogous of an alkene, like an elimination of an alkene to an alkyne. Remember when you did like, you brominate an alkene and then you do a double elimination and generate an alkyne? It's that same sort of, it's that sort of second elimination on the alkene, if you will. Okay? And again, now you've got a negatively charged species here, which can undergo the elimination. So again, this, I think from a standpoint of difficulty of this mechanism, this is certainly a difficult mechanism. I'm not going to lie and say I expect all of you guys to get this. I think when I gave this exam question on an organic 1 exam question, I think that maybe like 3 out of the 180 people got 10 out of 10. So I don't ask questions like this, and I'll reiterate, I don't ask questions like this expecting you guys to all be able to get the full question. What I ask a question like this is to pay attention to the intermediate steps. Did you get, if it's a 6-step synthesis to the product, well, if you got, say, for example, 3 in and then your mechanism fall apart, will the mechanism look okay through those first 3, right? Were you making those horrible mistakes that you guys got to break yourselves out of the habit of doing at this point, where, say, for example, you draw these arrows and you say that A goes to B, but the arrows that you show aren't illustrating that, right? Does that make sense? So you got to pay attention to each individual step, really focus on each of those individual steps. And again, maybe you'll come away with the right answer, but I guess the journey to that answer is infinitely more important, I think, than the answer itself, if that makes sense. Okay? All right, so this is certainly a hard mechanism question. But again, it's really just a Wolff-Kishner, right? It's a Wolff-Kishner. In fact, it's a Wolff-Kishner up to that elimination right there. So that elimination where you have an anion adjacent to an epoxide is probably the only thing that isn't something that any of you guys have seen, but yet that's simply an elimination and a variation of elimination. Does that make sense? Does everybody sees? Okay, maybe. All right, yeah. Yeah, you protonate that at the end. Yeah. During the aqueous workup. Yeah, yeah, yeah. So yeah. NaOH will eventually become H2O, and then okay. So again, I'm not concerned that many of you guys couldn't get this. I am concerned that you guys really struggled with the iminium condensation step. Okay, so I'm gonna scale back a little bit, and I'm gonna ask one more imine style condensation reaction, so hopefully a little bit easier. And I'm hopeful that now that we've gone through one, I'm hopeful that a larger percentage of you guys will get this. And this is in your book. It's not one that we've discussed, but it's in your book, and it's a variation of imine condensation. Okay, so it's enamine formation. Okay, so this is carbonyl reacting with an amine. And one of the only differences between this and imine condensation that we had in the past is that this represents a secondary amine, and so the product you're going to get is not going to be your standard imine. And so I want you guys to spend, the class is almost over, so let's spend 5 minutes. And then I'll go through the answer really quickly in the 5 minutes that we have remaining. Okay? So again, you guys should all be able to get partially through this mechanism, whether you can get to the end or not. If you're struggling with the first steps, that should set off some alarms in your head that you really need to step it up and really start focusing on the mechanisms. Again, your focus right now is on carbonyls. Overwhelming number of carbonyl reaction mechanisms involve condensation. This is simply a condensation reaction that is analogous to a lot of what you've seen. So I don't want to scare you guys, but you got to know this. Before I forget, just a quick announcement. So I mentioned first day of class that there was going to be 2 speakers. Well, we have lots of speakers coming by, but 2 speakers. Really 2 people that are visiting from other campuses. There's actually 3. One of my PhD students is going to be defending in a couple months as well. But the next 2 weeks, there are 2 synthetic organic chemistry speakers coming to give talks. And there's a new time for these talks. They're Wednesdays from 2:15 to 3:30, 1141 Ingersoll, which is, I think, first floor, like right when you walk in. You're going to be seeing postings of these around. This week, there's a chemist that I've gotten to know well through one of the conferences that we attend often. His name is Mingin Guy. And he's at Stony Brook, and he's a young guy. He's like, I think, in his 4th year at this point. He's just starting off. He's got really cool chemistry that he's going to talk about on Wednesday. So Ming is actually, again, is an assistant professor. The following Wednesday, we've actually got somebody coming named Dirk Trauner from NYU. And Dirk is actually much, much more well-established. He just moved to NYU recently from Germany. He was at Berkeley early in his career, ended up moving to a German university for a while, and then just accepted a job at NYU. He's a pretty big deal, and so he's going to be here next Wednesday as well. So again, I urge you guys to pay attention to these flyers, and if you can make it, I think it would be good for you to see. I can certainly be inspired to come up with questions based upon these lectures as well. So, all right. So the stuff is that. So yeah. So what you have there is or you can call the residence of that city shows so that's good up to the you're seeing yourself space right I probably would be like, oh, should you see space? I wasn't necessarily asking about that. But the fact you said you could get probably be like, oh. So if you're going to specify that in a way, specify it as you want. And if you want to be more specific, if you want some safe space, you just put one, step one, step two. So if you want safe space, you don't have to. Yeah, just this is probably a step one. Alright, so just a couple of announcements. A lot of people are doing the same mechanism, so I've already said a few times to a couple people, so I assume others are probably making the same thing. And that's, a lot of people are trying, again, I see the logic behind it. You see the alkene, and your first step is, let me get the alkene there. And so what they end up doing is they draw a mechanism that in essence shows the enol, right? So they go to keto, enol, quatameric form. And then what they try to do from there is they try to protonate and so more than a few people did this. And then they tried doing this to get to the product. So what's the problem? So I see the logic and the reason behind trying to get there, right? You're like, oh, let me get that alkene there, and then I'll simply replace the water with the nitrogen. What's the problem with this step here? There's a couple issues with that step. Yeah. So so you can't do eliminations, you can't do substitution. So first of all, you can't do substitution chemistry on an sp2 bond unless you start using like Yeomans or something like that. You don't do substitution SN2 on that kind of a system. So that's one of the big issues with it. We're sort of out of time, so we'll return to this. I want you guys to all go through this on your own. But the important point here is, yes, you need to have this nitrogen attack that carbon, but you don't attack it here. There's another step in the mechanism through which you do attack at that position. And again, we'll go over it on Wednesday, okay?